and sharing my screen. And before we get started, did anybody have any questions on anything that we did last class? If not, I'm going to, stop sharing and try to take this surface. And I think I'm in a better lit space this time. I'm going to put it here. I'm going to try to get the other computer and move it so that I can see what it looks like for you folks. Oh, that's no good. Nope. And plug this back in. And hopefully everybody has their spaghetti with them today. Whoops, moved. Jess, I got you on attendance. So we saw you in the waiting room. So
Okay, thank you.
We had gone through the construction for a congruent segment, looked at equilateral triangle, side, 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 and we didn't get to that triangle inequality because I apologize that I did not have my spaghetti with me. And so I'd like everybody to take a piece of spaghetti. And I want you to break it into segments of given lengths. So first I'm going to take it. First piece, I'm going to break off a piece that's 1 inch long. Then my second, I want to break off a piece that's 2 inches long. Then my third, I want to break off a piece that, can you guess, 3 inches long? And then a piece that's, well, 4 inches long. I'm going to just have a little bit left. And I'm going to make one more, a piece that's 5 inches long. And so I've got these 5 pieces of spaghetti. Their lengths are 1 inch, 2 inch, 3 inch, 4 inch, and 5 inch. So I'm going to take that 5 inch piece and let me take that 1 inch piece and that 2 inch piece. And can I make a triangle with
No.
side? No, they'll never meet, will they? Huh. What if I swapped out the 5 inch piece for a 4 inch piece? Will that make a triangle?
No.
No, huh? What if I swapped out the 4 inch piece with the 3 inch piece? They just meet, but they'd meet at a straight line. It won't make a triangle, will it?
No.
No. Why not? Because 1 and 2 equal 3. What if I took the 2 inch piece, the 3 inch piece, and the 4 inch piece?
Yes.
That works, doesn't it? Why does that one work? Because, go ahead.
Because the bottom side's longer than the top side and then the sides.
Well, 2 plus 3 has to be bigger than 4, right? It has to be bigger than the third side. The sum of any 2 sides has to be bigger than the third side. Because if it's not, they don't meet. Like if I took that 2 inches and 3 inches, well, 2 plus 3 just equals 5. And so that gives me a flat line instead of a triangle. But if I took the 3 and the 4, 3 plus 4 is bigger than 5. And so when the total of those two sides is bigger than the third side, they will meet with the triangle. So what the triangle inequality says, and I guess we didn't really have to play with spaghetti, but I think playing with the spaghetti kind of makes it much more tactile and easier to see why it's the case. Can you picture playing with spaghetti or sticks of some sort with elementary students to try to stress this idea to them?
Mhm.
So the triangle inequality, which I've had some classes refer to as the spaghetti theorem, says that the sum of two sides of a triangle must be greater than the third side. And I know somebody had said last class that that's just a little bit out of focus, and I have to apologize. I don't know how to focus it. Is that clear enough for you folks to see?
Yeah, with the marker,
Okay.
it helps.
I'm going to ask everybody to mute themselves so that the view that you mostly get is my screen, unless you're asking a question or answering a question. There's two types of questions that I will ask you and you will see with this. One is, let's say, if two sides of a triangle have lengths does anybody have a favorite number?
6.
6. And I need another favorite number.
8.
8. What are all the possible measures of the third side? And the way this is written, looking for all of those possible measures of that third side, does it make sense that I'm not just counting numbers? They could be fractions or decimals or anything in between. So here's where we need to pull on that algebra we developed in chapter 8. I'm going to let x equal the third side. The sum of any two sides has to be bigger than the third side. So that gives me 2 plus 8 is greater than x. So x has to be less than 10. But doesn't 2 plus x have to be greater than 8? And when I solve, don't I get x has to be bigger than 6? And the same way, doesn't 8 plus x have to be bigger than 2? But 8 is already bigger than 2, so I'm not going to worry about it. So I'm going to combine these two, and we can say that x has to be a value between 6 and 10. And I'm not just going to say 7, 8, and 9, because it could be 6.5 or 6 1/4 or 9.9. It just has to be any number in between those. Does that make sense to everybody?
I don't understand like the 2 plus 8 or like the 2 plus x. Like, where does the 2 come from? I just don't get that.
Wait a minute. I was using this too. It should be 6. I am so sorry, you guys. Thank you for saying that. That was my bad eyes. I'm sorry, my sides were 8 and 6, not 8 and 2. So I apologize. That should be 14, and that should be 2. And my answer should be that 2 is less than X is less than 14. Thank you very much for catching it. I just misread read the wrong number when I went through. I'm so sorry. Thank you for catching it. Better?
Yeah, thank you.
Okay. And then the other type of question you might have is, can the following be sides of a triangle? And let's say I have 7, 11, and 3. And I'm going to ask you folks, could those be the lengths of sides of a triangle? And why or why not?
No,
Why not?
because 7 and 3 are not greater than 11.
Beautiful explanation. Is everybody all right? The answer is no, because 7 plus 3 is not greater than 11. And the sum of any two sides has to be greater than that third side. And so that's that triangle inequality that we skipped over on Wednesday. Everybody okay with it? If so, let's go back and look at where we went from there. We constructed an angle congruent to a given angle by putting the point of our compass at the vertex, swinging an arc that crossed both sides, and then from the end point of a ray, swing that same arc. And then remember, we put the point at one point of intersection, the pencil at the other, made that arc, and then copied that arc here and connected. And then with that copying an angle, we got to another way of verifying that triangles are congruent by side, angle, side. And we said we constructed a triangle PIG. We copied a side. We copied the angle at P, and then we copied that other side, and we ended up with a congruent triangle. Next way we're going to see that we can get triangles congruent is ASA congruent to ASA, or angle side angle. And it says that two triangles are congruent if, notice we've got two A's, so we've got to have two angles and the included side of one are congruent to the corresponding parts of the other. And so to verify this, let's draw a triangle. And let's call this triangle CAT, and let's construct triangle DOG congruent to triangle CAT using angle, side, angle, congruent to angle, side, angle. And so in order to do this construction, I'm going to draw a ray. And C corresponds with D, so I'm going to put D here. Now, because we're using angle, side, angle, first thing I'm going to do is I'm going to copy angle C. So to construct an angle congruent to C, this is that last construction we did. I'm going to put the point of my compass on C. I'm going to swing an arc that crosses, whoops, swing an arc that crosses both sides of that angle and swing that same arc around D. And then remember we said it was important that we had 2 points of intersection. We're going to use both of those points of intersection. We're going to put the point of the compass at 1, and we're going to move our pencil so it exactly hits the other. We're going to swing an arc there. And then where we're copying the angle, we're going to put the point at where our arc intersected our ray and swing that same radius so that we have 2 intersecting arcs. I'd like to again say X marks the spot. That's where my treasure is. I'm going to connect that to D. And so now angle D is congruent to angle C, and that's my angle. Well, after we have an angle, it's ASA, angle, side angle. We want to copy a side. So I'm going to copy side CA. I'll put my point at C, swing an arc through A. Then I'm going to put my point at D and swing that same radius. And looking at the way I named them, A corresponds to O. So this will be point O. So I now know that segment CA is congruent to segment DO. I've got my angle and my side. Now for my other angle, because my side is CA and I've already got angle C, I have to copy angle A. That side needs to be in between the 2 angles. It has to be that included side is that side that's shared by those 2 angles. So that angle construction was so much fun. Let's do it again. I'm going to put my point at A. I'm going to try to make it so that the arcs don't overlap too terribly much. I'm going to swing an arc that intersects both sides of A. A corresponds to O. So with the point at O, I'm going to swing another arc of the same radius. Now, the only thing I have to measure how wide that angle is open is my compass. So I'll put 1 point at where the arc intersects one side of the angle. And I'm going to move my pencil and try to get it so that it's exactly at that other point of intersection. And I'm going to swing an arc there. And then I'm going to go and swing that same radius over where I'm trying to draw my new angle O. And again, that idea that X marks the spot, I want to, I guess technically I should be using a straight edge and not a ruler, connect that point of intersection to my point O. And if you notice, when I do that, intersects the other angle. That's the only point where that's possible. So that'll be G. And so triangle DOG is congruent to triangle CAT. All of the corresponding parts match, even though we only copied angle, side, angle. And so right now for congruent triangles, all three sides can match. And if that happens, we know that all three angles will also match, side, side, side. We have side, angle, side, two sides and the angle in between them. And now we have angle, side, angle, two angles and the side between them. Those three are pretty straightforward to verify with construction. But let's look and see what other possibilities there are. Over here, because I ran out of space, I crossed out it's AAS. AAS congruent to AAS is angle side. Side. So we'll say that two triangles are congruent if two angles and an opposite side let me move that up. I'm sorry, folks. Of one are congruent to the corresponding parts of the other. And this one's rather difficult to construct. So this one, we're going to just talk about the why of it. So I'm going to draw a triangle here. This will be triangle A, B, C. And then over here, I'm going to draw another triangle, X, Y, Z. Let's say that angle A is congruent to angle X. Angle B is congruent to angle Y. And this time I want a side that's not the included side. So let's say that side AC is congruent to side XY. Well, here I need a little bit of help. Can anybody remember what the total of the angles of a triangle always is?
60?
The sum of all three angles.
Oh. 180?
Right. The sum of all three angles of a triangle is 180 degrees. And so if A plus B plus C equals 180 and X plus Y plus Z equals 180, well, if A is equal to X and B is equal to Y, doesn't angle C have to be congruent to angle Z because of that?
Yes.
And so if two angles are the same, then the third angles must be the same. And so do you see if I have angle, side, because those third angles have to be the same, it's actually equivalent to angle, side, angle. And so to get triangles congruent, we're going to have these four ways. Can I turn the page and not lose anybody?
I have a question.
Sure enough, Emily.
On a test, Would you take off if the pictures aren't drawn to scale?
If it is a construction test, it has to be drawn accurately.
Oh boy.
Okay, your constructions, what I'm looking, when I grade a construction test, I have a compass in hand. And I'm checking, does this radius equal this radius? Does this radius equal this radius? Are your lines straight? I'm looking for those compass markings to be what they should be. I know at one point in time when I first taught this class, I had somebody who, after they did their constructions, they erased all the arcs because they thought they looked messy. I'm like, no, you can't do that. The only way I know whether you did the construction correctly or not is if I can see those arcs. So I'm looking for the arcs to be accurate. I'm looking for the lines to be straight. I don't think everybody was in class. At the beginning of class, I was talking about grading those activities from chapter 11 over the weekend. And some people did very wiggly lines and didn't use a straight edge and didn't measure with a ruler and didn't measure with a protractor and didn't draw circles with a compass. And so everything in their diagrams were off and it was impossible to give credit for them. You really need to start paying attention to trying to draw your things accurately.
I just can't get my pictures to look the same. Like that's my problem.
Can you stick around for a minute after class and share your pictures with me and I'll look at them with you?
Yeah.
Okay, great. So let's scooch on then. So we're going to say that to show triangles congruent, we can use, we've got these four: side, 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 congruent to side, 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 angle, side, congruent to side, angle, side, angle, side, angle, congruent to angle, side, angle, and angle, angle, side, congruent to angle, angle, side. So then what about angle, side, side, and angle, angle, angle? Both of those are no, they do not work. If I look at angle, 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 congruent to angle, 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 if I don't have any congruent sides, do you folks remember? That's going to make them similar, but not necessarily congruent. We need a side to know that they're congruent. Now that other one, angle, side, side, when I used to teach high school and did geometry proofs, I would write angle, side, side, ASS on the board, and I would get a plethora of giggles. And so if for no other reason, you can remember that it doesn't work because you don't want to be an ass. Angle, side, side does not work because it leads to something that's considered an ambiguous case. Sometimes if I have an angle and a side, let's say I have a length for the third side. This third side could meet here, but if I take my compass, couldn't that third side also potentially meet here? And so both those triangles there have the same angle. This side's the same. And these two sides are the same. And you see how that angle side, side could meet in more than one spot, which means there's more than one possible triangle. And so it does not work. So angle side, side will not give us congruent triangles, and nor will that backwards side, side angle will not work. It's that same combination. So you don't want to be a frontwards ass. You don't want to be a backwards ass. You can't use angle side, side. Everybody all right with that one? If so, the next thing that we're going to do is we're going to try to prove a theorem. The isosceles triangle theorem says that if two sides of a triangle are congruent, oh, let me move this up, I'm sorry. The angles opposite those sides are congruent. And we're going to try to verify this using what we know about triangles. We're going to start with a triangle, I guess will be boring, ABC. So we know that in triangle ABC, two sides are congruent. We'll say that AB is congruent to BC. And we want to use our vast knowledge of geometry to show that end statement, we want to be able to say that angle A is congruent to angle C. In order to do this, I'm going to add a point. I'm going to say that M is the midpoint of AC. Now I need some help. If M is the midpoint of AC, what does that tell me? What's special about a midpoint?
Put the segment in two congruent parts.
Beautiful. So can I say that if M is the midpoint of AC, then AM has to be congruent to MC because a midpoint divides it into two congruent parts. So far, so good.
Yes.
Now I want to draw BM. Once I draw BM, you see I took my one triangle and made it into two. And those two triangles, side AB is congruent to side BC. Side AM is congruent to side CM. And don't those two triangles share side BM? So can't we say that triangle AMB is congruent to triangle CMB by side, 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 congruent to side, side, side? Does everybody see that? And therefore, isn't angle A congruent to angle C because they correspond? And so we've shown that if we have a triangle with two congruent sides, then those opposite angles must be congruent. Thoughts? And that's one way of proving something's true. Next theorem that we want to look at, we also want to prove true, but this proof is going to be very much more algebraic in nature. This is going to be Thales' theorem, and Thales' theorem says that any angle inscribed in a semicircle is a right angle. Wow. Again, with these, we want accurate drawings. And so let's start by making a circle. And I don't want the whole circle. I just want half of it. So I'm going to draw a diameter. So I've got circle O, diameter AOB. So we can work with either side of the circle, the top or the bottom. I'm going to work with the top. I'm going to pick any point on the circle. I put it here, but I could have put it anywhere. I'm going to put that angle in the semicircle by connecting my point C to my point A and my point C to my point B. And this is supposed to be a right angle. Let's see. I'm going to compare it to my index card. Looks an awful lot like a right angle. And no matter where I put it, it should be a right angle. And we want to verify it. To verify it, I want to draw radius OC. Now, OA is a radius, OC is a radius, OB is a radius. So, doesn't it have to be the case that AO is congruent to CO is congruent to OB because they're radii of the same circle. So far, so good.
Yes.
Now, doesn't that mean that angle CAO is congruent to angle ACO? I'm going to call them both X because it's isosceles triangle. And I'm sorry, I'm doing a little bit of abbreviation because I'm running out of room. And doesn't this one also have to be isosceles? So doesn't angle OCB have to be congruent to angle OBC because I've got an isosceles triangle? I'll call those both Y. With me so far?
Yes.
Now, in the big triangle, triangle ACB, doesn't the measure of angle A plus the measure of angle B plus the measure of angle ACB have to equal 180? In the big triangle, doesn't the sum of the three angles have to be 180? Angle A is X, angle B is Y, angle C is that total X plus Y. That's 180. But combining like terms, doesn't that give me 2x plus 2y equals 180? And if I divide by 2, doesn't that give me x plus y equals 90? Or the measure of angle ACB is 90. How cool is that? And so we've got our right angle. And no matter where I had put point C on the circle, it would have always worked out that C would have to be a right angle. Isn't that a nifty little proof? Does it make sense, folks?
Kind of.
Okay. Now, let's go back to our constructions and let's construct an angle bisector. And does everybody remember that that bisector has to divide the angle into two congruent angles? And you've got the cookbook directions here, but let's go through and work through this together so that everybody can follow what those directions are telling me. So down at the bottom of the page, I'm going to draw an angle. And I want to try to come up with something that divides that angle into two congruent parts. All I can use is my straight edge, my index card, and my compass. Does it make sense? Because I don't see anything else I can do, that I'm going to put my compass so that the point is at the vertex of the angle. I'm going to try to tighten my compass so that it's not real wiggly wobbly. And I'm going to swing an arc that crosses both sides of the angle. Everybody got a picture that looks something like that? Now, I said it was important that my arc crossed the angle at 2 points. I'm going to make use of both those points. I'm going to keep my radius the same. I'm going to put my point at one of those intersections, and I'm going to swing another arc with that same radius on the interior of my angle. Everybody got that one down? Then I'm going to take my compass and I'm going to move my point to the other point of intersection. And I'm going to swing that same arc. And when I do that, do you notice that I get my X, my point of intersection?
How did you do like the like first, not the first compass line, but the second one? Like, how big did you make it?
I kept it the same radius.
Okay.
Okay.
Is it
So
like,
that-
is it wrong if, because when mine crossed, it wasn't in the center. It was like way,
Oh,
like
it could be
close
like
to
way out here. Right?
no, it was like really low to the first line. Like it wasn't in between the two, like
Okay.
it wasn't.
What's really important, Jess, is that this radius that I draw from this point of intersection and this radius that I draw from this point of intersection, these two radii have to be the same. You've got to
Okay.
make sure that your compass doesn't change.
Okay, thank you.
Okay? And the reason that that's important, well, first let me finish the construction. When I connect this, I should have divided that angle exactly in half. I'm going to check it with my protractor. And with my protractor, my original angle was, oh, it's kind of an ugly measure because well, that's right. So the numbers are right. It was just like 46 degrees. And it looks like it's crossing at 23 degrees. How crazy is that? The reason that it works is because I made sure that this radius and this radius are the same. The original arc made sure that this radius and this radius are the same. And so I've got side, 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 congruent to side, side, side. And so what I really did was I made two congruent triangles. But in doing so, we made sure that these two angles are equal in measure and we bisected that angle. So remember when we were looking at equilateral triangles, we said we could make a perfect 60-degree angle. Well, now, can't we cut that angle in half and make a perfect 30-degree angle? And can't we cut that angle in half and make a perfect 15-degree angle? So we can get some very precise angle measurements by just using our compass. And straight edge. I've got that it's about that time. So let's stop here. We'll pick up with the rest of our constructions on Wednesday. Any questions on what we've done today? If not, I'm going to pick up my so that you get that beautiful view of my ceiling. I'm going to stop recording.